Well, we're very happy to have Francesco Riva at, what is your local time?
10:30.
10:30 from Switzerland, so we should be kind to him. Francesco is at the University of Geneva, and he's going to be telling us about some limitations of effective field theory. So please take it away.
Possibly so. Let me share my screen.
Let me give you permission to share your screen.
That would be good.
Should work now.
Yeah. Okay. Do you see the little pointer?
Yes.
Yeah, we can see it.
Okay, good. Do you see the other stuff? I never understood this, whether you see the other Zoom things. Or...
We
No,
do,
you
but it's plenty big. We can see you fine.
Okay, very good.
You can if you want.
Okay, so thank you very much for inviting me. Yeah, as Marco said, I will talk about effective field theories, and in some sense, the topic will orbit around the idea of extreme experiments. Extreme in the following sense that when you first design and build an experiment, like I have in mind the Large Hadron Collider now, the beautiful expectation that you have is that you're going to discover something of this kind, something prominent that sticks out on top of a nicely predicted standard model background. In the end, as the experiment becomes more mature, the perspective also matures with it, and you enter this regime of precision experiments, precision physics, in which basically you're searching more for tiny deviations from your standard model, really trying to squeeze all the capability out of your experiment. And in this regime, the departures from the standard model are nicely predicted by a series expansion in powers of the energy, and this expansion is controlled by the energy over a putative heavy mass scale that in the context of searches beyond the standard model at the LHC, we attribute to some possible heavy new physics. So the message here is that physics searches for physics beyond the standard model are in one-to-one correspondence with the idea of effective field theory. And this is not only true in the context of colliders, but also in the context of quantum gravity and cosmology, and you name it. I mean, effective field theories are really present everywhere. Particularly, they emerge in any situation in which we can identify a heavy mass scale gapped from some low states. There in the infrared, you always have this idea of effective field theories that you can construct, and independently of what the high energy or UV reserves for you. The context in which effective field theories are particularly useful are when the UV is either uncalculable, like in the context of QCD, that at low energy becomes a chiral perturbation theory, or is even unknown, as is the context that I will have mostly in mind in this talk, in which we really don't know what it is, and we just want to understand its broad properties. So effective field theories are useful in a number of ways, but in particular, the way we typically think of them is that we want to distill some hypotheses in the UV and understand what do they imply in the infrared. For those of you who are have a foot in phenomenology, for instance, one context in which this has been used in recent years is understanding the couplings of the Higgs boson to the standard model particles, the W and Z bosons, or the fermions. And in particular, many of the hypotheses that we've been having about microscopic physics have been translated in this language of effective field theories. For instance, many of us know that in models of composite Higgs, the couplings of the Higgs boson to fermions typically can depart from the standard model in a similar way as that of the Higgs boson to vectors, and typically always by reducing with respect to the standard model. In supersymmetric models, instead, you have differences. The coupling of Higgs to the vectors is typically very close to the standard model. Here it's supposed to be the 0, and this is the experimental sensitivity that you have. And you can also think about many other models, some other BSMs, Z prime, or whatever, and all of them will have a correspondence in the infrared. But as you make this hypothesis broader and broader, eventually what you're thinking about in the UV is really quantum field theory in general. And so the question is no longer what can be learned from some UV model, but instead what can be measured in the infrared, because we're basically spanning now every possible quantum field theory realization in the UV. And this is a bit the kind of context in which I will be talking about, where the UV is any QFT. And the question is, what is the infrared? And the typical lore in the context of effective field theory is that any energy behavior in the infrared is consistent. For instance, if we're thinking of the 2-to-2 scattering amplitude for two particles, two scalar in the infrared, this is an expansion in the S and T parameters, at least at weak coupling. And so you can have coefficients for every possible term that you have in this expansion, every possible power of S and T. And these can have different sizes, one respect to the others in the appropriate units. As I said, in the common law in effective field theory, any of these hierarchies is in principle okay, in the sense that any hierarchy will find a UV matching from which it can emerge in the infrared. This is the law, but it's not true, as we have, many of you already know. But the question is actually to understand which of these hierarchies are allowed in if the UV theory has to be a quantum field theory. So if the UV theory has to be causal and unitary. And this will be the principal question that I will address in this talk. So assuming UV unitarity and causality, how does the effective field theory look like? And to keep you awake as much as I need, this is the type of terminology that you will see in this talk. A lot will be, well, everything will be fitting around the 2-to-2 scattering amplitude, and part of the talk will be a tree level where it's really just a polynomial. And coefficients have these names: C0, no powers of S; C2, no powers of S; C21, S squared T. And sometimes I will arrange them as a kind of table. So when you see C, I hope this helps kind of keeping track of what I'm talking about. Basically the bonds are going to be expressed in these quantities, and they are organized here. So in the first part of the talk, we'll discuss the tool to understand this UV-IR connection. These are dispersion relations. And we'll then tell you what the implications of this tool are for theories of weak or strong coupling. And finally, I will also extend this analysis that in the first part focuses on the forward scattering. And I will also extend to non-forward and show you some new results and application to the quantum gravity and gravity in general.
Hi, Francesco.
Yeah.
I have a question. Why does no term in the amplitude like starting from S?
Very good. Sorry. Yeah. It will be clear in the next slide. Now is a bit illustrative, but if it's the scattering of a single scalar, single flavor, then you don't have the S part. It's just because of symmetry and your amplitude. I'll get back to it in a moment. But basically, your amplitude is a function of S, T, and U. It has to be fully crossing symmetric. So it's a function either of S times T times U, or S squared plus T squared plus U squared, because the linear piece that you can build crossing symmetric is S plus T plus U, which is 0 in the massless limit. You see what I mean? Yeah. So
Okay.
it's crossing symmetry for a single flavor.
Okay.
Yeah, so it will, yeah, so in fact, what I will be doing is I will study really forward scattering, at least in the first part of the talk. So when really particles come in and go out, we'll be focusing on the simplest example, like a single spin zero particle of one flavor only. So that's why the three-level expansion, as you noticed. It's a function just of x in this case, because it's the forward one, t equal to 0. So the first step is to translate the physical properties associated with causality and unitarity into some mathematical properties for this 2-to-2 forward amplitude. In particular, causality is well known to imply analyticity of the amplitude in a complex S-plane up to some non-analyticity, some singularities, which are, however, always associated with some physics. In particular, rescattering of light particles. You can think now of pi 0 scattering. Its rescattering has an analyticity basically associated with the logs. When you have one loop diagram like this one, it comes with a log. The log has a branch cut, and this is what you see here. But in the UV, above the scale, which defines the end of our effective theory, there could be other forms of non-analyticity. For instance, the exchange at 311 of some UV particles that I don't know. So this non-analyticity here is out of control, but it must be here. Okay. Because of crossing symmetry, which is the fact that the amplitude is invariant when you exchange S and U, but S is also equal to minus U plus 4m squared because of S plus T plus U is equal to 4m squared, then implies that there is a branch cut also in the negative S part. And in addition, there are poles at the origin, just because I'm studying this object, amplitude divided by some powers of x. This is not so. I mean, it's important, but yeah, it's nothing big. Okay, so in this complex S-plane, it is divided in two parts. One in which we really have an effective field theory description is the region of small s, at least smaller than m squared. Here we have the effective field theory expansion, and we want to understand the red region. The blue region instead, I don't know what it is. As I said, it's either uncalculable or unknown. But I will only use the fact that unitarity implies that if the UV theory has to be unitary, the amplitude is positive across this branch. Then by using analyticity, I can connect this to region, because this contour must vanish, and Cauchy theorem tells me that this thing is equal to the big one. The big one vanishes for high enough, if I divide the amplitude by enough powers of n. Okay, so this really boils down to a equality between integral along these lines and the semicircle, and the discontinuity here is positive. Let me summarize what I just said. With a relation between this object, the integral along the arc, and an integral in the UV. This is unknown, and this is calculable within the effective theory. The radius of the arc will be called S bar. Sometimes I will use S hat just by mistake, but anyways, it's just to denote how big this is. So the object that I will be mentioning a lot in this talk is this arc, which is literally this integral along this contour of the amplitude divided by some power of S. Okay. And by the arguments I gave you, this is equal to an integral in UV. Now, the beautiful part of this, the integral in the UV is an integral over a positive quantity, because the imaginary part is positive. I told you before, it's due to unitarity and basically the optical theory. The imaginary part is proportional to the amplitude, the cross section, which is itself positive. Good. So this is positive. On the other hand, this is calculable. within the effective field theory. And to give you a spoiler, these arcs, when you compute them at 3 level, they're really equal to this Wilson coefficient, this coefficient of the energy that that appear in the amplitude multiplying powers of S, as Da asked a moment before, as one of those coefficients. So the good thing is that I can take the bound, which are positive, and import it in the infrared, just because of the equality here. And this becomes now a consistency check for our effective theory. All these things that you compute in your effective theory, they must be positive. This is a result that is due to Adams, Arcaniamed, Dubosky, Collins, and Vartazzi already some 15 years ago. And is this positivity that named then, I mean, it's due also to other people, but in this context, perhaps this is the most famous paper. And the name positivity is due to this fact. Now, the question I want to address here is whether there are more conditions that these arcs have to fulfill. Okay, positivity was rather obvious, but there are actually more that are less visible at the first glance. And they become more visible when you do a variable change, a rather trivial one. This is just 1 over S, actually S bar over S, I call it X. And then this integrand, I define a measure, a positive measure, which is swallows this imaginary part of the amplitude, which is positive. So this object now is equivalent to this other object, which we all know very well. This is it's called a moment in mathematics, and moments we're familiar with moments everywhere in physics. Moments of inertia, electric dipole moments, they all can be reduced to this form, basically. For instance, think of a stone or any 3-dimensional object, or 2-dimensional, if you prefer. In this case, you can think of d mu as the mass distribution of this object, extending over a radius r, and the zeroth moment, so the one where I put n equals 0 here, is just the total mass, the integral over d mu, the mass distribution, over the radius is really just the total mass. And this somehow sets the units of the problem. The first moment is integral of this times distance, and this is the center of mass, right? And the center of mass is maximized when all the mass is confined to one point in the external or in the maximal radius of this distribution. Okay. The second moment is the moment of inertia, and is maximized whenever the mass is on the edge of a ring, okay, or a sphere, if you are thinking in 3D. And this is always smaller than r square m. Okay. So why am I telling you this? I'm telling you this because you see that here we have 3 quantities: the mass, the center of mass, and the moment of inertia, and they are bounded by 2 quantities, the radius and the mass. So we already see that there are more conditions than just positivity, as we initially mentioned. Good. Can we do this a bit more concretely, a bit more extensively? The answer is yes, of course. And we already translated bounds on these arcs or Wilson coefficient with bounds on moments. And now I will argue that all the bounds on moments are in one-to-one correspondence with positive polynomial between 0 and 1. It's very easy to see this. A few formulas, but they are very easy to follow. Think of a polynomial that the coefficients are such that it is positive between 0 and 1. Okay. Then you just shower this polynomial inside this integrand with the measure d mu. So integral from 0 to 1 pn d mu. This is also bigger than 0 because the measure d mu is positive, right? And now by using the definition of these arcs as integral between 0 and 1 of d mu x to the n, we obtain a condition on arcs. Okay, so exactly equivalent to the one that arcs have to be positive. Arcs also have to fulfill a number of conditions, an infinite number of them, okay? So how to characterize all positive polynomials between 0 and 1? There are two useful characterizations that you can identify. One is super fast to see and to use. It's just polynomials made out of x to the n, 1 minus x to the n. Okay, this is clearly positive, this is clearly positive, so this is positive. Okay, and also summing these with positive coefficients will give you something positive. These are called Bernstein polynomials, if you ever came across this. So let me show you what these do. And I will be looking at this plane in which I'm looking at the first three arcs, so the first three moments, A1 normalized over A0, and S is just setting the units of, I mean, is the radius of this arc that I mentioned before. So the simplest polynomial is just X. Good. When I put polynomial of X in here, it just tells me that A1 is bigger than 0. So we have to be in this region. Another polynomial is X times 1 minus X, and it is this line. We have to be below this line, okay? Because it implies that A1 minus S squared A2 is bigger than 0. And you can go on like this, and when you put more and more polynomial, you see that you must be above this sentence and so on. And these are all linear conditions, so they're very easy to use. The problem is that you need actually infinitely many conditions before you can identify the plot for these three arcs, A0, A1, A2, okay? So in that sense, it's not so convenient. There's a different characterization of these polynomials, which is a bit simpler to use, which tells us that every polynomial positive between 0 and 1 can be written in this way, where Q is now a polynomial which is not positive. It's just a generic polynomial between 0 and 1, of which I take the square. Q2 also, Q3 also, and Q4 also. So for instance, take Q1 equal to just a sum of beta times X. As I say, this is not positive. Contrary to this one that had special coefficients alpha, this is generic coefficients alpha. When I take the square, I get a condition, and I use the definition of arcs. I basically find that this thing must hold, and this is the condition of positive definiteness of a matrix, this AI plus J. This is called a Henkel matrix. I will give you the definition in the next slide. But basically, this has to be positive definite. So this is very useful because it gives us now finitely many conditions for finite number of arcs, because I can take this polynomial just to go up to a certain power, and then I obtain conditions that only involve, for instance, in this case, arc A0, A1, and A2. Using this other method, I would always I will need to use infinitely many arcs, I mean, this approach that is closer to the idea of effective field theories. You only want to look at a finite number of coefficients. Okay, good. So all conditions involving finite number of arcs can be written as certain positivity condition on these Henkel matrices. Now I spare you a little bit of detail. Graphics is better. I'll give you the plots in a moment, but basically these have to be positive definite, and this is all you need. These are all the conditions on moments. For instance, up to 3 arcs, I showed you already the region that we have, and these are, it follows from just 3 conditions. So this is why I say this better, the right-hand side approach. We don't need infinitely many conditions, just 3. With 4 arcs, you can do the same as now this little volume here, and it's a very simple region to map out. So you see that any of the moments that I identified as arcs, and they actually have 2-sided bounds in limits of this A0 and N. Okay, so they're bounded below and above. So now I gave you a kind of mathematical understanding of moments and arcs, and the question now is, what do we do with this? Now we can compute, given an effective theory, we can compute the arcs in the infrared and see what these conditions are.
Sorry, can I ask a question?
Yeah,
Maybe maybe this is part of what you're going to say, but you know, we're very used to the idea that you know, if some coefficient in an EFT is too big, things go wrong. You know, we're used to this idea. But now you're showing that, okay, if I give you the size of one coefficient, okay, then the other coefficient can't be too small, right? I mean,
Yeah.
it sounds a little bit like, I don't know, a naturalness criteria, but here it's not naturalness that's going wrong. Something is really physically going wrong in the UV. I'm just wondering, do you have a more physical way of thinking about it?
You mean this idea that the next one cannot be too small? This is what we're referring to.
Actually, either one really, because even the unitarity bound is kind of, well, I don't know. I don't know if that's a correct physical understanding of this bound either, but I'm just saying I'm used to the idea of people telling me coefficients in an EFT can't be too big. I can sort of have a picture of what may go wrong there. But what is going wrong? Is there a way of thinking physically about what's going wrong if some coefficient is too small?
Yeah, good. Let me think. So you're referring to this kind of, because the one you referred before is basically the one above, right? When you say that the coefficient, well, it's not exactly this, but you're referring
the region above sort of seems like, I don't know, you know, like if I'm thinking of A0 as being given, then you know, then it says, okay, A2 can't be too big, right?
Yeah, A1 was being.
Actually, I guess it's also saying A2 and A1 both can't be too big.
Yeah. I mean, I don't know if this is the right way of seeing it, but you could see the fact that the coefficient E1 would renormalize. I mean, this we're talking about a coefficient C in the naming I used before. There is a normalization between these different coefficients. I don't know if this is the right way of seeing it, to be honest. I'm not 100% sure, but I could think that the loops involving twice this guy would this would the other way around, perhaps. Y cannot be smaller. So what goes wrong is that when you have two coefficients and two are of the same size, and the one in the middle cannot be smaller.
Yeah, it's kind of saying somehow they're not too far from each other in some sense, right?
Yeah,
it's qualitative.
Exactly.
What it's saying. Anyway, I didn't want to derail you. I just thought, I don't know what I'm really asking.
No, I understand. It's like whether we can I understand exactly what you're asking. To me, is even the usual unitary bound. I wouldn't call it. I kind of I'm seeing it in a different way now with these bounds. So yeah, I wouldn't be able to give you a simple physical understanding why this doesn't work. I mean, in examples you see it that if you exchange particles at 3 level, you cannot create this kind of things. For instance, I mean, if you integrate out a particle, right, the propagator is such that it doesn't allow for things to go down and then up again. So perhaps this can understand things that whatever you exchange, whatever state you exchange in the UV, if you think it in a narrow width approximation, the propagator that you associate with it when you can it doesn't really allow for things to go down and then back up. They either stay there or they keep on going down. And if you add more and more particles, you're never able to create this feature that something goes down and then up again.
I see, right.
Does this help a little bit?
Yeah, that's right.
Yeah.
Okay.
Good. Yeah, thanks for the question. It was very interesting. Okay, so the let me take the get into more concretely into the effective field theory, and in particular, I will start by looking at theory of weak coupling, in which the amplitude is really an expansion in powers of t, but since we are forward, it's just a polynomial in S. Okay. Then these arcs are integrals over the amplitude divided by powers of S, and this is really picking up the residue at some inverse powers of S, and there is a one-to-one correspondence between these arcs and the Wilson coefficients. So this is the simplest case. And what you see here is that weak coupling arcs capture every single Wilson coefficient. So basically, every coupling of the Lagrangian is captured by the arc, and we can really map, we can really understand the theory. Okay. On the other hand, check out what happens when, one more statement here is the fact that these arcs don't care about energy, in the sense that if you take the radius to be small or you take it to be big, they are independent of this. This basically implies the fact that this idea of weak coupling doesn't really, I mean, it's a fake, of course. Amplitudes have non-analyticities and laws, etc. This is really a regime which is valid only in a certain limit. When we actually turn on the coupling, so we make this thing bigger, what happens is that we have more features that appear in the amplitude. We have these logs that I just mentioned. By the way, this beta 4 here is just given by C2. There are more betas.
Sorry, can I?
Yeah.
Before you go to loops, I'm confused about this because I was wondering about this as well.
Yeah.
Let's just even stick to tree level in the EFT, and you can just ask, well, how does your bound depend on S bar? But see, I would have thought that the answer is that, you know, you've suppressed a lot of dimensions here. All these C's have different dimensions. And so if, let's say you think that theoretically you have some idea that there's a scale M that's physically important, and somehow naturally these C's should be compared with powers of M. But if M is where your theory literally breaks down, you should be taking S bar small compared to M. And then I would think the bounds you get are much weaker, because you would basically be comparing these C's in units of S bar. And so you would be getting much weaker bounds. So there's a trade-off. It seems to me that there's a trade-off between, if you want a really sharp bound, you have to take S bar small compared to M. But what you really want are the bounds for S bar equals M. And then that's only valid if the UV theory is weakly coupled.
That's a very good comment. Yeah, indeed. What you're saying is what you see here, that the units of this whatever, this flag, this banana, are S, or this hat, sorry, I forgot the hat here. But basically, it's the maximum energy at which you are trusting your effective field theory thing, right? And you're saying here you should take M square, right? M to the 4 in this case. Yeah, that's correct. In fact, is exactly what you said. I mean, the bound becomes more interesting when you take this thing big, and there is a trade-off of the fact that, well, you're really making the statement, I'm trusting this effective theory up to the scale. I can use these ansatz up to the scale, and there I trust these bounds. What I mentioned here about the energy dependence is just the fact that the arcs themselves, they don't depend on the energy. What depends on the energy is really the bounds that here carry units of energy in the bounds, because arcs with a different index, they are weighted. Yeah, when you compare them, they need energy because they have different units, so they enter different. But per se, the arcs they don't know anything about the energy. There's just a residue of, I mean, the coefficient of whatever power here of S. So you're right. I mean, this is something I'll come back actually in 1 second to it. I just flashed this thing on coupling, which I will take back at the end, but I'll come back in one slide to what you asked. Perhaps we can continue the discussion in a few seconds. So here I just wanted to show you what happens at strong coupling, but then I will pull this notion of strong coupling to the end. And basically what is the following. I pump up the coupling defined by this quantity, and the amplitude develops some non-analyticity given by these logs, and the arcs now, they become more complicated. They develop two types of features. Some are these are shown here by this dot. These are terms. Sorry, I'm struggling with this. Yeah, let me start with the red ones. Particularly, they develop some things which now become important at small s. So now in the region of small energy, the arcs depart from the coefficients, and somehow this makes some information inaccessible. On the other hand, so this implies that the window in which the theory can be taught as tree level, which the couple really shrinks. And there is also another effect that every other coefficient of the type of this beta, even the higher ones, they appear in these arcs. So really you have to make some assumptions to orient yourself at strong coupling. So we'll come back to this later. But I just wanted to give you an idea, because it's important to keep in mind that the story doesn't end at weak coupling. Everything becomes more complicated. But let me start with really focusing at the weak coupling. So the ansatz, my amplitude is. Yeah.
Sorry to interrupt again, but can I think of it like this? I could get a conservative bound by saying S bar is the largest scale where I think tree level is a good approximation.
Exactly. This is the perfect sentence to use.
Right. Yeah.
Yeah, very good. So the exactly, this is my amplitude, and let me think of this m square or s hat, whatever, as Marcus said, as the maximum energy at which I can trust this expansion. Okay. So the question I would like to understand, one of the first applications of this bound is the following. We know of many amplitudes in physics. For instance, I mean, Higgs scattering, lambda phi to the 4, bang, is just a constant. Plus and minus scattering, because of the z-pole in the S channel, it decreases with energy. We know of some cases that increases, but how fast can this increase? Because these increases are arbitrarily fast, at least in some regime. And naively, what you would think when you see an effective theory of this type, perhaps on the lines of what Marcus asked at the beginning, is that all coefficients are thought to be somehow comparable. And one reason we believe this is because C are mixed by running. In fact, if you start with coefficients that have this weird hierarchy, which is the one that we discussed a moment ago, in which it goes down at some point, running will tend to make things more homogeneous, and all coefficients would kind of look approximately the same. But this is not always true. There are some hierarchies between coefficients which survive running, so they are natural in some sense. And in particular, if you take this type of hierarchy in which lower coefficients are small and higher, more irrelevant coefficients are large, some units, this is okay. And this is okay because there is a symmetry to make this hierarchy natural. We're all familiar with the idea of a Goldstone that has a shift symmetry, pi going to pi plus alpha, a Lagrangian, which is derivative decoupled, and therefore an amplitude that starts with C2. So in the theory of Goldstone, there is no C0. But the thing goes beyond just the Goldstone. Galileans, they have an even more sophisticated symmetry. Pi plus alpha plus beta x. So now the Lagrangian is double derivative interactions, and the amplitude starts at S4, at least in some trivial, it's called trivial Galilean model. Galilean model is like you can extend this idea even further and concoct some symmetry with many powers of x. And then it's natural to have an amplitude that starts at a high powers of s, right? So we know that pi zero scattering has an S square dependence, but can it be even faster? Good. Let's grind this idea with our with the bounds that I've been showing you before. Arcs are in 1-to-1 correspondence with the Wilson coefficient, and so the idea I'm testing really this: can the amplitude grow faster than S square? When we look at this picture, now instead of the arcs, I really have the Wilson coefficients because arcs are in 1-to-1 correspondence with the Wilson coefficient, and in particular, the fact that everything leaves below 1 here means that the coefficient C4 in units of energy, it's always smaller than the C2 coefficients. These arguments don't apply to C0 because of this assumption that the contour at infinity vanishes required us to do some subtractions, and eventually the first coefficient of which we can say something is this C2. Anyway, C4 must be smaller than C2 in some units of energy, and C6 must be smaller than C4. So what the bounds are telling us is basically that whatever Cn you take, so whatever power of S you're thinking of, it just this region is just not compatible with the bounds. So when this amplitude becomes bigger than the S squared, sorry, the coffee, with the S squared piece, it just doesn't work. So this tells us the effective field theory only works here when C2 S square dominates. This I like very much this result because first of all, it's an information about the theory cutoff. It's telling us that any experiment you will ever do, you will never see anything growing like S to some power of n. Most you will ever see is S squared, because otherwise, I mean, otherwise you're at the cutoff. And it's also telling us this idea that I flashed to you before, that you can have this super soft symmetry, Galilean, whatever, they don't work. They have a cutoff which is so low that the idea of super softness is unobservable. Okay, so then operators with dimension bigger than 8 will never dominate. I mean, to many of you, this will not be a surprise. We always think of higher irrelevant operators as being suppressed. I opened the door a minute ago to the fact that perhaps they're not suppressed because they are natural because of this symmetry, but now I close this door again because they are incompatible with this bounds. Okay, so super.
I mean, you can, of course, observe it in the IR, right? I mean, in principle, just doing very precise measurements in the IR, you could convince yourself that it's the red curve and not the blue curve, right?
Yeah, you're saying that they are, I mean, you're saying, yeah, it's this piece.
Yeah, I mean, the fact that the amplitude can never get bigger than an amplitude with a normal Goldstone type growth, that's interesting, but it's not true that you could never imagine a super soft EFT describing some regime of nature.
Well, but you see, we'll never, to actually say that the thing is super soft, you will have to be in a regime in which this two can be thought of a kind of a small relevant perturbation with respect to this guy, right? Because if you do it here, I mean, any theory will have a S to the n, which is small, right? And every theory will have higher coefficients. But the question is where there is a theory in which these higher coefficients can dominate in such a way that the theory is really, the symmetry manifest here. Here, the symmetry is not manifest. You have a breaking which is bigger than the symmetry itself.
Oh, I'm sorry. Right. So the C, I think I misunderstood. Yeah, the C2 is actually there in the theory.
Yeah, yes, 2 is always there.
In the theory. Yeah, you're right. Okay.
Yeah.
I got it. I just didn't understand that. Thank you.
Yeah, sorry, it's telling you that C2 is always there and is always bigger than whatever comes after. Yeah, thanks for for allowing me to be more precise. Okay, very good.
Oh, okay, good.
There's one application of this that I like very much, which is higher spin resonances. This exists in QCD, nuclei, atoms, strings, whatever. And there's one fact that all these have in common. Higher spin, I'm thinking spin bigger than 2. Their mass is bigger than their inverse size. I mean, this is a picture just of the lattice higher spin resonances, and in particular, the ones here in orange are always heavier than large QCD, which is the size of one of the QCD resonances. It's possible that higher spin resonances were lighter. And well, the idea is that if you scatter these higher spin resonances, the maximum energy at which you can scatter them is given by their size, because this is how much you can localize them to do your scattering, right? And in fact, if you compute the amplitude for a scattering of higher spin resonances, it turns out that when you write a consistence effective theory, the amplitude looks like this. It has powers of S divided by the mass of the higher spin resonances to the power, some powers of J. Now, in the language that I've been using in this talk, this is C2 and this is C2J. And the maximum energy at which I can, so this is bound that we had before, and the maximum energy that I can use in this bound, the size is given by the size. You just solve this and you get that the mass of higher spin resonances is always bigger than the inverse size. So there is a kind of more fundamental reason why these guys are never light, because you really cannot write a consistent effective field theory to describe a higher spin resonance as a point part. Yes.
I'm keeping to bother you, but so I think there's something I missed here. I think your argument is that somehow for higher spin resonances, this amplitude, each of these terms up to S to the 2J are suppressed by M higher spin with coefficients of order 1. That's the basic claim?
Yeah. Yeah, that's exactly the claim. So the coefficient, as you say, are order 1, and the mass scale that enters here, it's really the mass of the higher spin. The way you see this, let me think. It's,
that's the thing I missed. Why should that be true?
Yeah, it is true. So the peculiarity of theories of spin higher or equal to 2, that self-interactions, when you build the theory, let me think how to explain this in a simple.
I guess it's related to the statement that there's no consistent theory where you can take that mass to 0, right? For spins bigger than 2, there's no such theory. The mass
and this thing goes up. Eventually, this is one of the manifestations of this.
Yeah,
exactly. Yeah, and
okay.
I mean, unfortunately, I don't have a sharper answer. It's a work I done a few years ago, and I lost the fluidity on building this effective theory. It's such a mess that you do it once and then this higher spin effective theory. But I can keep it in the back of my mind if I have a more intuitive explanation of why this is.
Okay. Yeah.
I mean, technically, the way you build these higher spin theories is that you have these extended gauge sectors, that then you also include the longitudinal degrees of freedom, and these masses they come out of this when you're actually looking at this is scattering of the longitudinal polarization, and similarly.
You got like goldstones of goldstones kind of thing, right? You got these.
Yeah.
Right. You need to. Yeah. Okay. It's fine. I think.
Yeah. It's the Stuckelberg thing eventually. That when you do it for spin 1, it turns out the mass cancels, but for spin higher than 2, the thing remains there.
Right.
Yeah. Very good. So, sure, I'm not doing okay. I still have a little bit of time. Let me talk you I'll start with this non-forward thing. Then you can tell me how you guys feel, and we can see if strong coupling is still on the menu or not. Okay, so far we've discussed just forward things in this of we've just looked at the amplitude at zero impact parameters. So the particles were possible, which is a rather trivial thing, but already we found a lot of things. Now, so the question is about pieces in the amplitude which are non-forward. For instance, coefficient of s squared t. If we take t equals 0, there is no bound this guy. The Galilean has different forms of Galilean. The one I mentioned before is called trivial. This one is not so trivial. It comes with a t. So the question is this thing actually excluded? And this is an important question, because this thing appears in massive gravity, in all forms of modified gravity. Cosmology is really a big player. And so understanding whether a theory in which this guy dominates is viable or not is an interesting thing for phenomenology, and the same for all the other guys here. So can we apply similar angular arguments beyond the forward limit? And I will show you now something which is in preparation. I mean, there are articles which discuss aspects of this, but the way I'm explaining to you is not appear yet. I think is the simplest way to explain in a seminar. You'll tell me later. I've given seminars in which I showed it different ways, and I don't think everybody has understood. You will tell me this is better. So we can assume now that the amplitude is analytic, not just at equal 0, but also at t different from 0. This apparently is something that it's proved to be true for when you scatter the lightest particle in the theory, but not in general. But still, So we don't have a formal proof that this is always true. At least in one case, which is probably the most interesting, in which we're really looking at the scattering of the lightest particle, we can trust this statement. So now I define an arc at t different from 0. What changed with respect to my previous definition of the arc is now the amplitude has t here. It's not just t equals 0, and also t here at the denominator. Okay, and similar to what we did before, we can do contour, blah blah blah, imaginary. But now I do one more thing, which is expanding the amplitude in the Legendre polynomial. Okay, fantastic. And the imaginary part of the amplitude of the partial waves is positive. Sorry, is positive for the same arguments. Now these arc here in the infrared now contains also these coefficients depend on t. In fact, they multiply t here. Now, as I said, there are many work on this thing, and they all differ by levels of complexity. But I think the simplest and the only thing that plays a role here is the fact that these Legendre polynomials are bounded. They're bounded for any n and any t to be between 1 and -1/2. I'll show you later a picture of how they're bounded, but it makes nice graphics. But let me show you what the implications of this boundedness are. This is, I mean, we all know that this is at most 1, and -1/2 is only because I'm keeping even L's. Otherwise, it would be -1. But it's not so important here. Anyway, what happens is the following. So in the infrared, we can plot this thing, right? This C2 plus C2, 1 times t. This is just a line where steepness depends on C2, 1, and then the place where it meets here is C2, okay? And in the UV, I can also plot this thing, because this thing, as I say, is always smaller than 1. And the units of this integral that I'm plotting in this axis is really the arc at 0. So when you take t equals 0, you get 1 here for the polynomial, and you don't get the thing here. So it's really the expression we were looking at before. So this is telling us that this arc must live within this trumpet. Okay. Now, to be honest, here I show you the linear approximation, but in fact, there are many more terms. It turns out that these many more terms you can bound them with the bounds I showed you in the previous slide. I can tell you more details on this, and okay, it makes a kind of an error band around my line, but still, this is calculable in the infrared somehow. Okay, so the name of the game is comparing UV with the infrared. So this trumpet must sit in the big trumpet. Okay, fantastic. So we see the upper bound is when this is about to exit from above, and it's really telling us that this thing is bounded from below in units of C2. Or C2 is always setting the units in the end. It's a bit like the mass in the stone example. And when but now I also get a bound on the bottom. Sorry, now I also get a bound on the bottom part that really, if you want, the previous bound here was still at t equals 0, but this one is really at t. On this axis I have t, if I specify it. And this is really another bound that comes at finite t, and it's roughly 5 when this touches the thing. You can be a bit more precise. I will show you later on even more precise. Is around 5. And basically, it's telling us the same message, that this Galilean, as defined here, has a small cutoff. I mean, there's a factor of 5, it's not a 1, but for what concerns an effective field theory, this is really small in these units. By the way, I promise you I will show you these Legendre polynomials. They are shown here. These are Legendre polynomials. This is L, and in this little video, I'm varying x. This is, sorry, x, t, basically, I'm moving along this line, right? And you see, the red line is really, sorry, we also have this black thing here. Oops. Anyway, no, okay, so before I was just telling you that this is more than 1, this is the red line here, and bigger than -1/2, okay? But if you look at the video, you see that the lower bound is actually, is even better than the yellow one. This -1/2 actually is too conservative. We can do better. And it turns out that if you really want to do better, that's how you get this 5.17. But sorry, you get more information out of it, which is the fact that the bound is saturated by the partial waves with L equal 2 or 4. Why is this exciting? This is exciting because not only you're getting a bound, but you also know why there is this bound. This is bound because if in the UV theory you have particles of spin 2 or 4 at threshold, then this is the bound you get. If you happen not to have those particles, or they are heavier, then your bound would be even more conservative. So somehow, this way of doing the bounds, they also keep tight relation with what you have in the UV, the particle content in the UV. Good. Hope I have not made you faint in this thing. There's a lot of details, but let me. Okay, this is an even. Let me have this. This is a small summary of what all these bounds are in terms of these coefficients that I mentioned before. Well, the first one, I never said anything about it. Is the coefficient like lambda and lambda phi to the 4. No information of this because of this. We need to subtract the amplitude by powers of s in order to have bounds. C2 is positive, the coefficient of s squared, and every other coefficient bounded from below and above. Okay, so this is the situation we have with all these bounds. Now, the last application, which is due to this t equals 0, is exactly this idea of massive gravity. Let me show you quickly how it works. So we all know about gravity, right? It's a theory of us from a particle physics perspective, is the theory of a spin-2 particle with no mass, 2 degrees of freedom, and described by Einstein-Hilbert action. And when you scatter 2 gravitons, the amplitude goes like s over over m Planck square at high energy. And therefore, it's a theory that is valid up to the Planck scale, okay? Now, massive gravity is a completely different beast. Now you have more degrees of freedom. And in particular, typical mass that you're interested in when you talk about massive gravity is something of order of the inverse Hubble scale. This is for two reasons. First, because if this is the case, it might address the cosmological problem, and also because experimental bounds on the graviton mass are of order this scale. So what happens when you give the graviton a mass, you add a part of the potential, and it turns out that the amplitude goes like S over the mass of the graviton square. This is what we were discussing before in the context of high spin. You always have this masses hitting at the denominator. Okay, it's a pretty bad theory because its validity, cutoff, is given roughly by the denominator here, and this is the biggest possible scale in our universe, a distance scale. So we went from the smallest possible scale to the biggest possible scale. Sometimes this is referred to as the appearance of a ghost. Were it not for the fact that along almost a century, people realized that by tuning the coefficients potentially not so understood way at the beginning, basically you can alter this picture and you can get your massive gravity to be valid up to at least planetary scales. And amplitude now has this form. Now this is what I call C2 so far. This is what I call C21. And in fact, if I apply now these bounds that I showed you before on the C1, they were in units of C2 and energy, so the cutoff, it turns out again, the typical maximal energy at which I can operate is of order the graviton mass. So again, we're back to this picture. So the message is that massive gravity, the idea is not compatible with this unitarity bound. Okay, I think I already used up my time. I had some comments on strong coupling. Let me skip through. We can come back to this if you're interested. If you have more questions that touch this. Sorry, there are animations. So they prevent me to go fast to the conclusions. But sorry, put this to 10 seconds. Okay, good. So to conclude, the picture I tried to paint was one in which the reality is divided into the infrared and the UV. And in the UV, we only we know very little, but we think the theory must be called unitary and Lorentz invariant. And then I showed you how this idea of moment was useful to constrain the affected field theories that we get in the infrared. And in particular, the fact that of all the coefficients of an affected theory, there are only a handful, like two, I don't know why I wrote three now, sorry, that can dominate. This is probably what you already were thinking when you entered the seminar room, and I'm happy to confirm this prejudice. There's nothing better than having a prejudice confirmed again, right? But to get to this, as I said, I opened the door of the idea of super softness that somehow would allow any coefficient to be dominant. Super softness doesn't exist. Higher spin don't exist, a limit which they look like point particle, and massive gravity, if you are conservative in how you think about their UV completion, also doesn't exist. All right. That's it. I show you also some things about the running and the fact that strong coupling messes with this bound, but didn't give you any details. Thanks a lot for listening and all the questions.
Yeah, thank you very much. Anyone besides me have any questions? Any questions from Zoom world? Is anybody still there? We can't see you, but there you are. I mean, I have some questions, but I'm happy. We usually, if you could, I don't know, Francesco, if you can stick around a little bit afterwards.
I'm
should-
fine.
you're
I
Okay.
think I overdid with the coffee, so I have all the time of my life.
All right. Well, anyone last chance before we? Okay, let's stop recording and let's thank Francesco again and we'll continue some informal discussions without the recording.